Today we will continue our lecture 1 on real analysis by covering induction. So we're just gonna have induction. So right now n, the natural numbers, has a ordering ordering 1 is less than 2, which is less than 3, which is less than 4. Axiom, or like a statement which we don't need to prove. Well ordering property of the natural numbers. If set S is a subset of N and S is not an empty set, then S has a least element, or there exists an X in S such that X is less than Y for all Y in S. Only the natural numbers has this special property, and the reason is because when you move on to the integers, the least number could go all the way to negative infinity, but in the natural numbers we know it's 1. And if S is a subset of the natural numbers, then it also has a least element. So this is just the well-ordering property of the natural numbers. So we're gonna define this as VOP. Theorem. Let's talk about induction now. Induction's a technique to solve proofs. So let P of n be a statement depending on n in the natural numbers. Assume base case P of 1 is true. An inductive step. If P of m is true, then P of n plus 1 is true. So the two things we need to do when proving a statement: prove the base case if the statement with the 1 works, and this one where P of m and P of m plus 1 work. Now let's prove induction. I'm actually only going to do like one proof or two with induction. Okay, so basically, let S be all the properties, all the numbers in n, such that P of n is not true. So, to prove induction, we're going to prove that this is actually nothing. So, now we're going to prove this by contradiction. It's basically, you're proving that the statement is true is false. Like you assume the statement's false and then come to a false statement. So you contradict. Negation of statement is true and then arrive at a false statement. So here's the actual proof. We already wrote that, said that S equal to all the numbers in N such that P of N is not true. We need to assume that S does not equal to the empty set and derive a false statement. Rules of logic says that S, which is not the empty set, but suppose S is not the empty set. By the well-ordering property, S has a least element, X. Since P of 1 is true, 1, which is not an S, or whatever, my notes are not working. X is not in 1. X is not 1, okay? So X is not 1. In particular, X is greater than 1. Since X is the least element of X, and X minus 1 is less than X, then X minus 1 is not an S. Obviously. By definition of S, Px minus 1 is true. By number 2, P of X is true. So X is not an S. So how is that possible? So from the well-ordering property, S must be empty. We already defined this as the least, but if the least is not in there, then it just has to be empty. The two statements collide. Okay, so now we're going to use induction. We want to prove for all natural numbers which satisfy P of N, and for all natural numbers, P of N is for all N in natural numbers, P of N is true. True. Base case. And P of M is real and P of M plus 1 is true. It's a theorem. Now this is going to be a P of N. For all C not equal to 1, and for all N numbers 1 plus C plus C squared plus C to the N equals to 1 minus C and plus 1 minus C. So now we're going to prove P of N, P of 1, base case. So obviously if N is 1, then it's just this, and obviously this equals to 1 plus 1 minus C, 1 plus 1 plus 1 minus C, since 1 minus C squared divided by 1 minus C equal to 1 minus C, 1 plus C. So we're basically just factoring it out here. So base case is proved. Now the inductive step, the real juice. Assume P of N. We want to prove that our first statement, which I'm going to denote by star, 1 plus C squared all the way to Cn, holds for n equals to m plus 1. So we have this statement over here. Which can be factored into or defactored. So by induction, P of n holds for all n. Oh, wait, 1 minus c. So this is over here. Remember, n plus 1 equals to n. So this is the same statement as which is what you needed to derive. So by induction, P of n holds for all n in natural numbers. Holds for all n in natural numbers. Bye, everyone.